Hello everyone, welcome to the first video in our mini-series about CPU scheduling algorithms. In this series, we will break down different algorithms into simple terms while showing examples and explaining how they work in real systems. Don't forget to keep an eye out for new videos in this playlist. Each one will explore a different CPU scheduling algorithm in detail. So, let's get started. First come, first serve is a concept we encounter almost every day. Think about lining up at the cashier in the department store, waiting to buy food in the school canteen, or even standing in line for clearance signing at the end of a semester. In all these cases, the rule is simple. The first one to arrive is the first one to be served. Now, how does this idea translate into CPU scheduling? Well, it's the same, but instead of people waiting in line, we have processes or tasks waiting in a queue. The CPU serves them in the order they arrive. Whoever comes first gets executed first. And because first come first served is non-preemptive, once a process starts running, the CPU will not interrupt or switch it out unless it is finished. New arrivals must wait their turn. Now that we understand the basic idea of first come first serve, let's look at how we represent it in practice. One of the most common tools we use is a process table. This table helps us organize important information about each process, like when it arrives, how long it needs the CPU, and other details we'll calculate later. It's basically the starting point for analyzing how the scheduling algorithm works. For example, in our table, we will list each process, its arrival time, and its burst time. Now, I'll briefly display these definitions so you can clearly see what each term means before we move on to solving with examples. Please do take note of them because they will appear again in the next episodes as we explore other scheduling algorithms. A process. It is a program in execution, a task that needs CPU time to run. So basically, it means a job waiting to be done by the CPU. The next one is arrival time. The moment a process enters the ready queue and is ready to be executed. So basically, it means when the process shows up in the line. Next is burst time. The total amount of CPU time a process needs to finish running. Basically, it means how long the process takes to run. Now that we've seen the process table, the next step is to visualize how the CPU executes these processes. For that, we will use a Gantt chart. We take the arrival times and burst times from the process table and place each process on the chart in the order they are scheduled. This way, we can track the CPU's activity step by step. So I'll now display the Gantt chart for our example processes so you can see how the scheduling looks in action. So as you can see, process P1 starts first at a time 0 and runs until time 4. Next, process P2 begins at time 4 and runs until time 7. Then, process P3 takes over at time 7 and runs until time 11, completing all processes in the queue. So what this chart shows us is the timeline of CPU activity. Each process gets its turn in the order it arrived, and once a process starts, it runs until it finishes. This makes the Gantt chart a powerful tool for visualizing scheduling and preparing to calculate values, like the waiting time and turnaround time. So now that we've built the Gantt chart and can see the order of execution, the next step is to calculate some important values that help us measure the performance of this scheduling algorithm. The two key values we'll focus on are the waiting time and turnaround time. Waiting time. This tells us how long a process spends waiting in the ready queue before it gets to the CPU. So basically, it means the time a process spends just waiting for its turn. The next one is the turnaround time. This is the total time taken from when a process arrives until it finishes execution. So basically, it means the overall time a process spends in the system. So now that we have the Gantt chart, we can start calculating the performance values for each process. I'll display the Gantt chart below so we can use it as a guide while solving, because it shows the values that we need, like the start time, the completion time, and the arrival time. So the first value is the waiting time, and the formula is waiting time is equal to start time minus arrival time. This tells us how long a process spends waiting in the ready queue before it gets to the CPU. So for example, the waiting time for process P is equal to the start time, which is 0, minus the arrival time, which is also 0. So the waiting time for P1 is 0. This means that process 1 or process P1 didn't have to wait at all. It was served immediately when it arrived. Next is turnaround time, and the formula is turnaround time is equal to completion time minus the arrival time. This gives us the total time a process spends in the system. Now for example, the turnaround time for process P1 is equal to the completion time, which is 4, minus the arrival time, which is 0, so the turnaround time for P1 is 4. This means that process P1 spent a total of 4 units of time in the system, from the moment it arrived until it was fully completed. Now that we've finished the calculations, let's analyze first come first served algorithm by looking at its strengths, weaknesses, and where it works best. Now, first, FCFS, or first come first serve, is simple and easy to implement. It doesn't require complex logic, which makes it straightforward to use. It is also fair. Processes are served in order they arrive, just like lining up in real life. However, one major drawback is the convoy effect. If a long process arrives first, it can delay all the shorter ones waiting behind it. This means that FCFS is not ideal for systems that need quick response times like interactive applications. Instead, it's better suited for batch processing systems, where jobs are handled one after another without needing immediate interaction. You'll also see FCFS used in print queues, where documents are printed in the order they arrive. And finally, it can be effective in simple operating systems where fairness matters more than speed. So to wrap things up, first come first serve is one of the simplest CPU scheduling algorithms. The first process to arrive is the first to run. We saw how it works using the process table and the Gantt chart, calculated the waiting time and turnaround time, and analyzed its strengths and weaknesses. While FCFS is fair and easy to implement, it can suffer from the convoy effect and isn't ideal for systems needing quick response times. Thank you for watching and following along. I am Harley Asvale, and stay tuned for the next episodes where we explore other CPU scheduling algorithms.